Okay, welcome back again to one more lecture on analog circuits, subject code 18 EC42. So this is lecture number 36 or the lecture number 6 of module 4. So today in this lecture we are going to discuss about some numericals on non-inverting and inverting configurations, which we have started in the previous lecture. And also we'll start with the applications of opamp, and we'll try to analyze how the opamp plays a vital role in getting the things done easy through its various applications. So to begin with, I'll share the contents what we have done in the previous class. Yeah. So in the previous class, we try to get through the concept of voltage shunt feedback amplifier, wherein we saw the expressions for closed loop gain. We solved the expression for input resistance with feedback, and then an assignment was assigned to you with respect to the output resistance of voltage shunt feedback amplifier. And then we saw how the input resistance derivation can be quickly done with the help of Miller components by breaking the RF into its two subsequent components, thereby obtaining these equations. Then we arrived at voltage and feedback amplifier's bandwidth equation, which resembles almost same. Now, one thing that I just want to highlight, or I just want to mention here would be, yeah, so as you can see, there's a comparison chart which I have shared over here. Now the comparison chart says there's a non-inverting amplifier and an inverting amplifier with the different voltage gains, gain of the feedback circuit, input resistance, output resistance, and on the bandwidth, and total output offset voltage. Though we haven't done this thing because that was not mentioned. We have done various derivations with this with respect to these aspects. Now, if I just put them beside and try to compare them properly, this is what I'm going to get. Hold on for a moment. There's some issues with my network. I'll just correct it for just 5 seconds. Yeah, so I was talking about the comparison. Am I audible?
Yes, sir.
Yeah. Now you can see we have just now in the previous class we derived the voltage gain expression for the inverting amplifier. That is the exact equation, and I was telling about how you can remember the things. That is, only in the numerator part there is a slight difference. Adu bitre bare ಏನು difference ಇಲ್ಲ. In the inverting amplifier it is minus A times RF. In the non-inverting it is A times R1 plus RF. So that is what is the difference. And this is the exact derivation. Now here one thing they have mentioned, that is, as you can see here, this expression. Normally we started our entire exercise or entire concept of feedback amplifier, and we obtained an equation of the voltage gain or gain, and that gain equation with feedback was AF equal to A divided by 1 plus A beta. So ಇದೇನ್ equation ಅದಲ್ಲ, this is the standard equation. Standard equation ಅಂತಂದ್ರೆ ಯಾವಾಗ ನನ್ನ ಸರ್ಕ್ಯೂಟ್ ಅಲ್ಲಿ ಆರು resistive components ನನಗೆ ಗೊತ್ತಿರಂಗಿಲ್ಲ, or I just say that there is an voltage amplifier and all the resistive networks or all the components which form the feedback network is represented by the term beta. ಅಲ್ಲಿ ನಾನು ಸ್ಪೆಸಿಫಿಕ್ ಆಗಿ ಹೇಳಂಗಿಲ್ಲ ಬೀಟಾ ಅಂದ್ರೆ ಏನು ಅಂತ, right? So hangagi my general equation will be always A divided by 1 plus A beta. You remember this. So this is the general equation of any amplifier with feedback. Now the same thing here in inverting amplifier, it is also the same thing, A divided by 1 plus A beta, but with a small inclusion of one element, which is your K. Now K here is nothing but the attenuation factor. Inverting amplifier olagade, there is an attenuation that is going to happen, and what is the amount of attenuation that gets added? So that is just reflected in the equation. Though nanu both for inverting as well as non-inverting configurations, A divided by 1 plus A beta will be my standard equation. Or feedback amplifier anta bandaga nan gain equation A divided by 1 plus A beta adu fixed. ಈಗ ಎಕ್ಸಾಕ್ಟ್ ಇಕ್ವೇಶನ್ ಅಂದ್ರೆ ಏನು? ಎಕ್ಸಾಕ್ಟ್ ಇಕ್ವೇಶನ್ ಅಂದ್ರೆ ಏನು? ಎಕ್ಸಾಕ್ಟ್ ಸರ್ಕ್ಯೂಟ್ ಇರುತ್ತೆ. ಐ ನೋ ವಾಟ್ ಈಸ್ ದ ಸರ್ಕ್ಯೂಟ್ ಆಫ್ ಮೈ ಆಂಪ್ಲಿಫೈಯರ್, or I know how exactly my circuit looks. I know which is my input resistance, which is my feedback resistance, or I know what are the components that are present in the feedback path, or I know how exactly the feedback is taken from the output. I know everything. ಅದನ್ನ ನಾನು ತಲೆಗಿಟ್ಟುಕೊಂಡು when I started doing the derivation, and once I obtain the gain equation, that gain equation looks this way. That is my exact equation. Please be very careful in these things. When you say the terms exact equation and circuit exact other, this is your general equation, right? Now exact we have done, we said that AR1 times is much greater than R1 plus RF. So R1 plus RF nanu ignore ಮಾಡಬಹುದು, or I can nullify it. So ಏನಾಗುತ್ತೆ, A divided by AR1 ARF ಮ್ಯಾಗ ಆಗುತ್ತೆ, ಕೆಳಗಡೆನು AR1 ಆಗುತ್ತೆ. So those AA cancelled out, and what is that I obtained? I obtained a new equation 1 plus RF by R1. This equation is your ideal equation, and this is what you have done in your basic electronics course or in your any previous course. So till date you have been explored to only these ideal equations. Now it is the exact equation. How you obtain the exact equation? Or exact equation is nothing but a resemblance of this general equation only. General equation ಅಂದ್ರೆ general circuit ಇರುತ್ತೆ, circuit ಇರಂಗಿಲ್ಲ, block diagram ಇರುತ್ತೆ. Exact equation ಅಂದಾಗ exact circuit ಇರುತ್ತೆ. So that is the difference. So this is my exact equation, this is my ideal equation, and the same is the case with the inverting and inverting exact equation and inverting amplifiers ideal equation. Now what was the gain of the feedback circuit, or the beta factor? What was the beta value that we obtained? The beta whatever the value we obtained was, or the value of beta what we have sensed from my circuit is R1 divided by R1 plus RF. That's what we have obtained. And what was my input resistance? Here we have obtained when it comes to non-inverting amplifier. So this is my non-inverting. Yeah, when it comes to non-inverting amplifier, the input resistance what we have derived is input resistance. ಅದೊಂದು ತಲೆಗಿಟ್ಕೋರಿ, input resistance ಯಾವತ್ತೂ ಜಾಸ್ತಿ ಇರಬೇಕು. ಸೊ ಜಾಸ್ತಿ ಇರಬೇಕಪ್ಪ ಅಂತಂದ್ರೆ ವಿತೌಟ್ ಫೀಡ್ಬ್ಯಾಕ್ ಇನ್ಪುಟ್ ರೆಸಿಸ್ಟೆನ್ಸ್ ಎಷ್ಟು ಇರ್ತೈತಿ, ವಿತ್ ಫೀಡ್ಬ್ಯಾಕ್ ಅದಕ್ಕಿಂತ ಜಾಸ್ತಿ ಬರಬೇಕು. ಸೊ ವಿತೌಟ್ ಫೀಡ್ಬ್ಯಾಕ್ ನನಗೆ RI ಇರುತ್ತೆ. ಸೊ ವಿತ್ ಫೀಡ್ಬ್ಯಾಕ್ ಇಟ್ ವಿಲ್ ಬಿ RI times 1 plus A beta. So that's what we have derived the equation for my the input resistance equation considering the non-inverting configuration. And the same thing we did in the inverting configuration, and there we did by applying the Miller's concept, and we obtained a very simplified, very quick equation, that is R1 plus RF divided by 1 plus A in parallel with RI. So this is my RIF equation when it comes to inverting amplifier configuration. And I was talking about the ROF, which I have assigned you as an assignment, and I was also telling you in my previous class the equations resembles exactly the same thing. As you can see, ROF ನಾವಿಲ್ಲಿ ಯಾವ ತರ derivation ಮಾಡಿದೀವಿ, in the same manner you keep on doing the derivation. The only difference ಏನು, circuit change ಆಗತ್ತೆ. ಸರ್ಕ್ಯೂಟ್ ಚೇಂಜ್ ಆಗತ್ತೆ ಅಂದ್ರೆ ಏನು, ನಮ್ಮ ಇನ್ಪುಟ್ ಇಲ್ಲಿ ನಾನ್ ಇನ್ವರ್ಟಿಂಗ್ ಟರ್ಮಿನಲ್ ಕೊಟ್ಟಿರ್ತೀವಿ, ಇಲ್ಲಿ ಇನ್ವರ್ಟಿಂಗ್ ಟರ್ಮಿನಲ್ಸ್ ನ ಕೊಟ್ಟಿರ್ತೀವಿ, ಅಷ್ಟೇ ಚೇಂಜ್ ಆಗತ್ತೆ. ಆಮೇಲೆ ಇನ್ನೊಂದು, why this ROF remains same, ಯಾಕೆ ಸೇಮ್ ಉಳಿತದಪ್ಪ? When RIF is not remaining same, then how come ROF is remaining same? I'll tell you the reason. RIF ಯಾಕೆ ಸೇಮ್ ಉಳಿಯಂಗಿಲ್ಲಪ್ಪ ಅಂತಂದ್ರೆ ಇನ್ಪುಟ್ಸ್ ಆರ್ ಡಿಫರೆಂಟ್. ನೋಡ್ರಿ, ನಾನ್ ಇನ್ವರ್ಟಿಂಗ್ ಆಂಪ್ಲಿಫೈರ್ ಒಳಗಡೆ we are giving the input to non inverting terminal. Inverting configuration ಒಳಗ we are giving the input to inverting configuration. But output resistance ಕಂಡುಹಿಡಿಯಬೇಕಾದ್ರೆ what is the first step I do? I will short the input voltage. So input voltage, or I will just connect the input voltage or remove the input source and connect it to ground. ಈಗ ನನಗ ಇನ್ಪುಟ್ ಸೋರ್ಸ್ ನೇ ನಾನು ಗ್ರೌಂಡ್ ಕನೆಕ್ಟ್ ಮಾಡಬೇಕಾದ್ರೆ ಅದು ಇನ್ವರ್ಟಿಂಗ್ ಟರ್ಮಿನಲ್ ನಾಗಿದ್ರೆ ಎಷ್ಟು, ನಾನ್ ಇನ್ವರ್ಟಿಂಗ್ ಟರ್ಮಿನಲ್ ನಾಗ ಇದ್ರೆ ಎಷ್ಟು. ಸೊ ಅಲ್ಟಿಮೇಟ್ಲಿ ಮೈ ಇನ್ಪುಟ್ ಹ್ಯಾಸ್ ಗಾನ್ ಟು 0 or it has been eliminated. ಹಂಗಾಗಿ my ROF value will be exactly same when you talk with respect to either inverting configuration or non-inverting configuration. So that's how the equation will remain same, and that's what I have given you as the small assignment towards deriving that particular equation. And then I also said the bandwidth of my non-inverting amplifier, which is my voltage series feedback amplifier, which we derived earlier, and we have understood the entire aspect of break frequency and bandwidth yesterday. The bandwidth was f0 times 1 plus a beta. So normally without feedback iddaga f0 will be my bandwidth. F0 bandwidth ಅಂದ್ರೆ ಏನು, ಇದೊಂದು gain bandwidth graph ಇತ್ತಪ್ಪ ಅಂತಂದ್ರೆ, so e particular point where there is a 3 dB dip, so that is my f0. So this is the particular frequency till which the gain is constant. So ನಾನು without feedback ಇದ್ದಾಗ ಇಷ್ಟಿತ್ತಪ್ಪ ಅಂತಂದ್ರೆ, with feedback ಇದ್ದಾಗ ಈ f0 will be shifted towards the right side. That is how much amount? 1 plus AB times it will be shifted. So my new equation or new graph of my the gain bandwidth graph looks something like this. So illivargu hogodu. So that will be my new f0, and that I call it as ff. So that is my the bandwidth, which is an extended version. So bandwidth basically jasti agata when it comes to feedback. And again, why it is again same in terms of non-inverting. So inverting non-inverting configuration doesn't have to play a crucial role with respect to bandwidth. Ultimately both are feedback amplifier, and we have seen that feedback amplifier ittappa antandre bandwidth jasti age agata. Adu ಎಷ್ಟು part jasti agata, it is going to get in terms of 1 plus a beta, 1 plus a beta times jasti agata. So in that way my bandwidth for my inverting as well as non-inverting configuration is again going to remain same. And to be specifically in terms of unity bandwidth equation number ff is equal to UGB times AF. Here I write ff is equal to UGB times AF multiplied by K. And what is this K? K is a factor. Just how you obtain the value of beta R1 divided by R1 plus RF, K also can be obtained as RF divided by R1 plus RF. So R1 divided by R1 plus RF beta kotre, RF divided by R1 plus RF, you will give the value of K. And finally they mentioned something about output offset voltage, though this concept is not there. I'll just give a glimpse. Offset voltage just if the maximum at the output side will be the saturation voltage, whatever we have been specified in the datasheet, divided by 1 plus a beta. So that's what will be the total offset voltage with respect to both inverting as well as non-inverting configuration. Now with this, let's try to just jump into a small problem which we started in the previous class, and let's start with can you see the same problem snippets what we have started in the previous class? Let's go ahead and look. In the previous class we started with what is the percentage change in the loop, and our problem, the interpretation in what was the reason for doing that particular problem is to prove that gain with feedback is very very stable. So gain with feedback equation ನಾನು AF is equal to A divided by 1 plus A beta ಅಂತ ನಾನು ಏನು ಮಾಡ್ತಿರ್ತೀನಿ. So ಆ equation ಒಳಗಡೆ if any changes happen to your if any change happens to your open loop gain, that is not going to hamper the closed loop gain equation. So this is what is the interpretation what we have done in the previous class. So moving on with one more problem. An inverting amplifier shown in figure 4, which is over here, with R1 equal to 10 ohm, R2 equal to 1 mega ohm, is driven by a source V1 equal to 0.1 volt. Find the closed loop gain A, the percentage division of A from the ideal value R2 by R1, that is minus R2 by R1, and the inverting input voltage Vn for the cases A equal to 100 and 10 raised to 5 and 10 raised to 5. So both are same. So a lot of things have been asked. Let's try to get into the things in a typical manner by breaking the components into small aspects. So first of all, find the closed loop gain. So this is an inverting amplifier. So inverting amplifier, just now we figured out the equation minus RF by A divided by R1 plus RF plus AR1. So adu nandu closed loop gain equation. So that I have written over here, and upon that I'm going to substitute all the values. RF, what he has given, RF he has given, here it is RF in the figure itself, it is 1 mega ohm. this has to be 10 raised to 6. So by mistake it is typed as 10 only. You make it as 10 raised to 6. So this will be 10 raised to 6. A est kotanama gain, that is open loop gain. For the one case he has given 100. For one case he has given 10 raised to 5. For the other case he has given 10 raised to again 10 raised to 5. Yeah, fine. So for the case, I think he has taken when a is equal to 10 raised to 3. Yeah, maybe this could be 100 but 10 raised to 3 ಆಗಬೇಕಾಗಿತ್ತು. Yeah, 10 raised to 3 ಇದ್ದಾಗ ಎಷ್ಟಾಗಿತ್ತು. So a value 10 raised to 3. Okay, this should be 10 raised to 3, and RF is what, 1 mega ohm. RF 1 mega ohm he has typed that properly. A he has taken as, instead of 10 raised to 3 he has taken as 10. Okay, ಇದನ್ನ 10 raised to 3 ಮಾಡ್ಕೊಂಡ್ರೆ and it will be 10 raised to minus 10 raised to 9. Whole divided by R1. Again he has given, he has taken that value. Where is my R1? R1 is here. That is 10k, and RF is what? Feedback resistance 1 mega ohm, and A into R1. A is 10 raised to 3, and R1 is, I think he is doing a lot of mistakes over here. In one portion he is taking A as, yeah, A is 10 raised to 3 and R1 is also 10 raised to 3. Yeah, that's fine. That's correct. So if I take 10 raised to 3, 10 raised to 3, and I multiply that, once I take that, both the numerator and denominator, if I do the division and if I do the simplification, so this is what I'm going to get. So AF is what? Minus 497.5. So nan AF, this is my practical value. Nanaga AF ideal value bekappa antandre, what is my ideal equation? Ideal equation is what? Minus RF by R1. Minus RF by R1 na madre enagatte. What is RF? RF is 10 raised to 6 and R1 is 10 raised to 10 into 10 raised to 3. If I do that simplification, it is only 10 raised to 3. Look at the difference. AF with feedback, and I mean that is exact value, and AF an ideal value. Both are completely different, and we always try to take the practical value into consideration. Now he has asked what is the percentage deviation. ಈಗ previous example ನಾಗ ಏನ್ ಕೊಟ್ಟಿದ್ದಾವ, previous example if I just take here, ಅಲ್ಲಿ deviation ಹೆಂಗ್ ಕೇಳಿದ್ದಾವನು, he changes the value of gain. ಏನಂದಿದ, ಫಸ್ಟ್ ಗೆ a ಒಂದು ವ್ಯಾಲ್ಯೂ ತಗೋರಿ, ಆಮೇಲೆ ನೆಕ್ಸ್ಟ್ ಟೈಮ್ a ಇನ್ನೊಂದು ವ್ಯಾಲ್ಯೂ ತಗೋರಿ. ಈ ಎರಡೂ ವ್ಯಾಲ್ಯೂ ಚೇಂಜಸ್ ಆದಾಗ, a ವ್ಯಾಲ್ಯೂ ಚೇಂಜ್ ಆದಾಗ ಎಷ್ಟು ಪರ್ಸೆಂಟೇಜ್ ಡಿವಿಯೇಷನ್ ಆಗಿತ್ತು ಅಂತ ಕೇಳಿದ. ಈ ಎಕ್ಸಾಂಪಲ್ ನಾಗ he is asking you ideal value ಮತ್ತು non ideal value or ideal value ಮತ್ತು exact value ನಡುವ percentage deviation. Look here, in the question he is asking the percentage deviation of a from its ideal value. So ideal value ಮತ್ತು exact value. So ideal value is 497.5, exact value or actual value is, sorry, ideal value is 10 raised to 3, exact value is 497.5, and if I do the division, I'm going to get the result as 50.25%, and that's what is my the final value. And what is the final output you are going to calculate? How you are going to calculate? Output is nothing but input multiplied by gain. Gain 497.5, and what is the input? Input for various values of input. If I take Vi as given as 0.1 volt, so if I take that particular value, input 0.1 times the gain, so that will be my output voltage. So that's how I solve my equation and obtain the output voltage. And the same thing is repeated for different values of A. So this is one typical example wherein the inverting amplifier configuration values are given, and you are supposed to try to find the different values of gain and do the comparison. So this is one set of problem wherein you are supposed to use simply the gain equation, wherein for different values of A, how would be the percentage change from its ideal value or and from the practical value. This is one A problem or one kind of problem. Second kind of problem ಏನು ಮಾಡಿದವ, A value ಒಂದ್ಸತಿ ಒಂದ್ ಕೊಡ್ತಾನೆ, ಇನ್ನೊಂದ್ಸತಿ A value ಚೇಂಜ್ ಮಾಡ್ತಾನೆ, ಅವು ಎರಡರ ನಡುವೆ ವಾಟ್ ಈಸ್ ದ ಡಿವಿಯೇಷನ್. ಸೊ ಈ ಪ್ರಾಬ್ಲಮ್ ಏನಿತ್ತು, ಐಡಿಯಲ್ ಮತ್ತು ಪ್ರಾಕ್ಟಿಕಲ್ ವ್ಯಾಲ್ಯೂ ನಡುವೆ ಎಷ್ಟು ಡಿವಿಯೇಷನ್ ಇತ್ತು ಅಂತ ಕೇಳಿದ್ದ. ಇನ್ ದ ಪ್ರೀವಿಯಸ್ ಪ್ರಾಬ್ಲಮ್ ಏನ್ ಕೇಳಿದವ, ಐಡಿಯಲ್ ಮತ್ತು ಪ್ರಾಕ್ಟಿಕಲ್ ಅಂತ ಕೇಳಿದ್ದಿಲ್ಲ, ಪ್ರಾಕ್ಟಿಕಲ್ ವ್ಯಾಲ್ಯೂನೇ ಕಂಡುಹಿಡಿಬೇಕು, ಬಟ್ ಎ ವ್ಯಾಲ್ಯೂ ಚೇಂಜ್ ಆದಂಗ ನನಗೆ AF ವ್ಯಾಲ್ಯೂ ಹೆಂಗ್ ವೇರಿ ಆಗುತ್ತೆ. ಸೊ that was asked in the previous problem. So this is all about this one and two second kind of or second category of problem. So let's move ahead with one more kind of numerical. I'll try to share one more thing over here. So Let's try to do that. Yeah. So this is the same screenshot which I have taken from the textbook. That's what I was mentioning in my earlier class. Example number 3.1 and example number 3.3, which I'm going to solve here in the class. So let's go with example number 3.1. The 741C opamp having the following parameters is connected as a non-inverting amplifier, figure 3.2. That is whatever the figure we have taken out. So basically this is a non-inverting amplifier. So the amplifier what we have designed in the very beginning of the class. So where it is? Yes. So this is the circuit. So E circuit, see, the moment he says non-inverting amplifier or inverting amplifier, you should have the figures, respective figures in your mind. So basically you should remember the figures and the equations properly. Just to keep aside the actual content and give you some glimpse about examination. So this module being very easiest of all the modules, let us try to ensure you gain maximum expertise in this particular module and try to see that whatever are the concepts that are covered in the class, you pay utmost attention and try to grab the concepts properly and try to attempt these concepts with utmost skill in the examination. So e concepts opamps concepts starting this entire module agbodu. So now almost half the module is done, and then remaining half the module is nothing but dealing with the different applications, which are very simple and very easy to understand. In another 3 classes, we could be able to finish up those applications as well. So those applications and owing to these 2 set of derivations. Here set derivations yaudappa ಒಂದು non-inverting amplifier, that is the voltage series feedback, and one there is inverting amplifier, which is your voltage shunt feedback. So you add a derivation ಮತ್ತು ಅದರ respective problems. So if you are thorough, then definitely all the entire module will become a cakewalk. So that's what is my intention. So please remember this figures properly whenever you start writing the or solving the problems, and please don't run away from the problem, because problems will hang over. If you do step by step, there will be marks allocated for different steps. So ನಿಮಗೆ ಇಲ್ಲಿ ನೆನಪಿಟ್ಕೊಳ್ಳೋದಂತದ್ದು ಎರಡು ಮೇನ್, ಒಂದು equations, that is the gain equations. ಅದು ಬಿಟ್ಟರೆ ಮತ್ತೊಂದು ಏನೂ ಇಲ್ಲ, ಬಾಕಿ ಎಲ್ಲ automatically it will follow the things, right? So let's go ahead and let's see what he has given here. R1 value kotanama. So R1 value is here, this one he has given, and then RF value he has given, that is the feedback. Open loop gain A he has given, that is 2 lakh, that is 2 into 10 to 5. RI 2 mega ohm. What is RI? Input resistance of the opamp here inside he has given, right? Fine. And then R0 he has given 75 ohms. R0 will be somewhere over here, that is output resistance of the opamp. And then F0, that is 5 hertz, that is your break frequency, which means the bandwidth he has given, and supply voltage he has given, and finally he has also mentioned output voltage swing. I just want to highlight one aspect. ಈಗ output voltage swing plus or minus 13 voltage ಅಂತ ಏನು ಕೊಟ್ಟಾನವ. So what is that indicates? ಇದೇನು ಇಂಡಿಕೇಟ್ ಮಾಡುತ್ತಪ್ಪ ಅಂತಂದ್ರೆ, see, one thing you remember, gain ನಾವು 2 lakh ಅಥವಾ 2 into 10 to 5 ಅಂತೀವಿ, ಅಥವಾ 100 to 200, we say a lot of numbers in terms of gain. ಹಂಗಂತಂದ್ರೆ ಒಂದು ಸ್ಮಾಲ್ ಇನ್ಪುಟ್ ಕೊಟ್ಟಂದ್ರೆ ಅದು ನಾನು 200 volts 300 volts ವರೆಗೆ ಆಂಪ್ಲಿಫೈ ಮಾಡಬಹುದಾ? And if I do that, my entire problem of my complete electricity problem will be solved. ಆಗ ಮಾಡಬಹುದಲ್ಲ? But the thing is, there is always a limit to that particular device. ಆ ಡಿವೈಸ್ ಗೆ ಒಂದು ಥ್ರೆಶೋಲ್ಡ್ ಲಿಮಿಟ್ ಅಂತ ಇರುತ್ತೆ. So that threshold limit is the maximum voltage, or up to what voltage it can amplify. So up to a maximum of supply voltage it can amplify. ಅಂದ್ರೇನು? ಈಗ ನನ್ನ ಇನ್ಪುಟ್ ನಾನು 1 millivolt ಕೊಟ್ಟೆ, and I gave the gain as let's say 1 million, and I'm expecting an voltage to somewhere around 100 volts. But ನನಗೆ ಆ opamp ಗೆ ಸಪ್ಲೈ ವೋಲ್ಟೇಜ್ 15 volts ಕೊಟ್ಟಾಗ ಅದಕ್ಕಿಂತ ಜಾಸ್ತಿ ಆಗಿ ನನಗೆ ಔಟ್ಪುಟ್ ಬರಂಗಿಲ್ಲ. ಐ ಆಮ್ ಗೋಯಿಂಗ್ ಟು ಶೋ ಯು ದಿಸ್ when we talk about the comparator circuits in the application sections ಅಲ್ಲಿ ಹೆಂಗ ನನ್ನ ಔಟ್ಪುಟ್ ವೋಲ್ಟೇಜ್ ನನಗೆ ಔಟ್ಪುಟ್ ವೋಲ್ಟೇಜ್ ಬರೋಣ ಅದು ಹೆಂಗ್ ಕ್ಲಿಪ್ ಆಫ್ ಆಗುತ್ತಾ ದ ಪೀಕ್ಸ್ ಆಫ್ ದ ಸಿಗ್ನಲ್ಸ್ ಕ್ಲಿಪ್ ಹೆಂಗಾಗುತ್ತೆ ಅದು ನಾವು ಅಲ್ಲಿ ನೋಡಬಹುದು. ಬಟ್ ಪ್ಲೀಸ್ ರಿಮೆಂಬರ್ maximum voltage or maximum level of the amplification that can happen is restricted by the supply voltage. And on top of that, there is one more parameter that will be mentioned, that is output voltage swing. So 15 voltage tananu correct amplify agilla, adakkinta slightly less amplify agutta, and that is what is my output voltage swing. So up to a maximum of minus 13 to plus 13 volts or peak to peak voltage to ondaga 26 volts vargu it can amplify. So this is the basically the things that these output voltage swing and supply voltages give us. Now what he is asking us to compute the values of AF, RIF, ROF, FF and VOT. I'll come to this, what exactly VOT, let's not worry about that. So these are the things that he is asking. Fine. Now let's first try to calculate the value of beta, because beta is that term which is always going to play a crucial role, because it is the feedback network. Nangilean network adala, that is my beta. So beta, if I can find and if I can get the values of the things, so that will give me a complete idea of what exactly will be the values. Just hold on for a moment. Yeah, so that was some disturbance that was happening. Fine. So beta, what was beta? R1 divided by R1 plus RF, that's what is here. R1 divided by R1 plus RF, because feedback now non-inverting amplifier togobekara across R1 nan in voltage bartade, that is my feedback voltage. So whatever is the voltage across R1 is my VF. So either the parallelly or the voltage division happens something like this, R1 divided by R1 plus RF. So adanna madadaga what is that I'm going to get? Simply substitute the values, I'm going to get 1 by 11. R1 is 1k, R1 is 1k plus 10k, 1 by 11. And let's try to calculate 1 plus A beta, because that is what I'm going to use in my equations. A he has already given as 2 into 10 raised to 5. Beta, just now you have figured out, 1 plus this whole term divided by 11 will give you a value of 18182.8. So that's my 1 plus A beta value. Okay, fine. Now let's try to calculate the AF. What he has told, first thing is to calculate AF. Okay, now what is the equation of AF should I use? Now if you can just look over here what he has used. Illi here he has not told you to calculate exact using an exact equation or ideal equation or a general equation. You are free to use any equation. So what he has used, he has substituted 2 lakh divided by 18, 182.8. So what is the formula you think he might have used? It is A divided by, he has used A divided by 1 plus A beta. So this is the formula he has used, 1 plus A beta, which we already figured out. A value has given, and if I do that, AF will be 10.99. Now let me ask the question, sir, can I use the equation of this one? Can I use the equation of this? Definitely you can use this equation, and if you do this, use this equation and solve it, you are going to get the same value what he has obtained over here, and you can just cross verify that. And I'll be giving you as this as a part of assignment as well. Try to cross verifying with respect to different values. Simple equation. Fine. AF value bant nanaga. Then what he has asked to find RIF. So RIF equation in it nanaga. If I just look over here, RIF, RI multiplied by 1 plus A beta. So that is the reason I am asking you to figure out what is 1 plus A beta. Again, I first 1 plus A beta value calculate my. So RI is what? Ri multiplied by 1 plus A beta. 1 plus A beta is already calculated. Ri he has given as 2 mega ohm, and if I do the substitution, I'm going to get the value as 36.4 giga ohm. And look here, what is the huge value it has obtained? That is, the input resistance with feedback is 36.4 giga ohm, whereas input resistance without feedback is merely 2 mega ohm. So that's a huge difference that you can see by imparting feedback concept in any of the amplifiers. So that's the beauty of the feedback concept. Finally, what is ROF? ROF equation we just wrote over here, RO divided by 1 plus A beta. So RO, what he has given? He has given RO as 75 ohm, which is over here, and 1 plus A beta you already calculated. So that's the reason I am asking you to repeatedly to keep it a value of 1 plus A beta always handy. And if I do this simplification, I'm going to get the value as 4.12 milli ohm. And can you just see the difference? RO without feedback is in terms of ohms, 75 ohms ಅಂತ ಐತಿ. RO ಅದೇ RO when you impart the feedback use ಮಾಡಿದ ಕೂಡಲೇ RO will become ROF. So ROF the new value ಏನದ 4.12 milli ohm, which means it is even smaller than this 75 ohms. Again, that is one of the beauty of imparting the negative feedback or the concept of feedback towards the amplifier. So ROF value is 4.12 milli ohm. Fine. Now let's just move on to the aspect of FF, that is the break frequency with feedback, or basically the unity gain bandwidth. So what was the equation? It is F naught times 1 plus A beta. What is the equation of FF? F naught times 1 plus A beta, which is over here. I can see over here. So the same equation he has used. F naught is 5 hertz. He has mentioned over here. F naught is what? 5 hertz multiplied by 1 plus A beta. That gives you a bandwidth of 90.9 kilohertz. And look at the bandwidth. Whereas the earlier bandwidth was having a value of only 5 hertz. Now the new bandwidth has got a value of 90.9 kilohertz. So this is how the bandwidth is increased automatically by imparting the feedback. And finally, the output offset voltage, whatever he has told you to calculate, this was what I was mentioning, total output offset voltage. The formula was V sat divided by 1 plus A beta. You can substitute that as well and figure out, though this concept is not there for your syllabus, but you can just remember. And plus or minus indicates this could be of either polarity. Now he gives here one small note over here. In the above example, the voltage gain calculated using the exact equation is 10.99, and the gain would have been 11 if we had used the ideal voltage gain equation. Thus the difference is very small and can be ignored. That is, for all practical purpose, we may use the ideal voltage gain equation, provided that A is very, very larger than AF. Right? Okay, and remember that as AF approaches A, the difference error also increases. See what he says. In the for all the practical purposes, if A is very, 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 very large as compared to AF, then I can use a simply ideal voltage gain equation. Ideal voltage gain equation ಏನಪ್ಪ 1 plus RF by R1. ಅದನ್ನ ನಾನು ಯೂಸ್ ಮಾಡಬಹುದು. ಅದು ಯಾವಾಗ? When the open loop gain is very large than the closed loop gain. So at the time the difference error will be very, very less. So that is what he is given the footnote. Fine. So that's all with respect to the non-inverting amplifier problem. Now let's just move on to next problem or next numerical, which is nothing but your inverting amplifier of figure 8.3. Again, that figure is nothing but inverting amplifier, which we have dealt in the previous class, which is over here. Yeah, so this is what is my inverting amplifier structure, what we have dealt in the previous class. So yeah, so this figure he is referring, and he is asking us to calculate different values. Let's just go through the problem. For R1 equal to 470 ohm, RF equal to 4.7 kilo ohm, assume that the opamp is a 741, that is a 741 IC, having the same specifications as that given in the previous example. Now he is asking us to calculate the same thing: AF, RIF, ROF, FF, and forget about this VOT. Let's not worry about this. But the difference here is Sati, in rather than giving the non-inverting configuration, he is giving us inverting configuration. So in inverting configuration problem solve ಮಾಡಬೇಕಾದ್ರೆ just one thing you should remember here, the value or the aspect what we calculate with respect to K, attenuation factor. So beta will be R1 divided by R1 plus RF, K will be RF divided by R1 plus RF. ಏನಪ್ಪಾ ಅದು attenuation factor ಅಂತಂದ್ರೆ, like whenever we talk about the amplifier, when output is getting back to the input through the feedback, there is a one feedback resistor and there is another R1 resistance. So R1 resistance ಒಳಗಡೆ ಮತ್ತು RF resistance ಒಳಗಡೆ ಏನು voltage division ಆಗುತ್ತಲ್ಲ, ಒಂದು voltage input ಕಡೆ ಹೋಗುತ್ತೆ, ಒಂದು voltage it will be loss. So it leads to the attenuation in the feedback. So attenuation factor ಎಷ್ಟಪ್ಪ ಅಂತ identify ಮಾಡಲಿಕ್ಕೆ he has taken up this particular equation. So our equation I should always remember, and specifically in the inverting configuration only. So in the inverting configuration, again let's follow the same principle and calculate the value of K and beta. So K is RF divided by R1 plus RF, and beta is R1 divided by R1 plus RF, and do the calculation. If I do the calculation by substituting the values, I'm going to get the value as K is equal to 1 by 1.1, beta is equal to 1 divided by 11. And please ensure you calculate the value of 1 plus A beta, because that gives you handy information in quickly calculating the things. So 1 plus A beta will lead to 1 plus A is what? 2 into 10 raised to 5. He has already given. He says it is the same thing that is used in the previous example. And beta is what? 1 by 11. And if I do that calculation, 18182.8 is my 1 plus A beta value. So I obtain it. So let's try to find the gain equations. What is the gain equation now? AF in terms of opamp, ಇಲ್ಲಿ ಏನ್ ಮಾಡಿದ್ವಿ ನಾವು? A divided by 1 plus A beta ಯೂಸ್ ಮಾಡಿದ್ವಿ. ಇಲ್ಲಿ ಅದೇ ಜಾಗದಾಗ A multiplied by K divided by 1 plus A beta. So A multiplied by K, so this is my K and this is my A, whole divided by 1 plus A beta. So this is 1 plus A beta, which you already calculated. So if I do these things and calculate, and my AF value will be minus 10. So this is what is my AF value. And on the same line, so if I just go ahead and calculate RIF will be, just look over here, what is my RIF here? R1 plus RF divided by 1 plus A in parallel with RI. So this is what we have done in the previous class, the derivation. So other equation I use martini, R1 plus, it is RF divided by 1 plus A beta, RF divided by 1 plus A beta, 1 plus 1 plus A, it is not 1 plus A beta, 1 plus A, and 1 plus A is of course 1 plus 2 lakh. That doesn't make any sense, so I can just ignore that one. That's what he is has just taken 2 lakh or 2 into 10 raised to 5 in parallel with, what was the value? RI. So RI value has given, RI value is given as the same as the previous example. So what is RI value? 2 mega ohm. So let's say 2 mega ohm, he has taken that. So upon solving all these things, either division madri in parallel with this, and try to be acquainted with the calculators, these divisions, the parallel and series combination aspects, this plays a very crucial role in the numericals. The division madi, and if I do the parallel equation, if I solve it and I add it to this, whatever the value, I'm going to get the output is the input resistance with feedback almost equal to the same value. If I do the simplification, you're going to get almost equal to over 70 ohm. So that's what I calculate with respect to RIF. Now finally let's go ahead with ROF. What is ROF? ROF is what? RO divided by 1 plus A beta, and I have told you that is not going to change. RO divided by 1 plus A beta. So RO is 75, 1 plus A beta is already calculated. This I'm going to substitute over here, and finally I'm going to end up in getting the value as 4.12 milliohm. And finally FF value pertaining to your inverting configuration, it will remain same. that is UGB, that is unity gain bandwidth divided by AF, but the only thing that added over here is K terms will get added. So basically UGB and then now F0 times 1 plus A beta. So UGB and F0 times 1 plus A beta. That's what the other UGB and so the other name F0 times 1 plus A beta. F0 is 5 hertz, which are already is given. 1 plus A beta you already calculated. Difference in a whole divided by K. K value is 1 by 1.1, which you have calculated over here. Adna substitute madi and you get the value as 100 kilohertz. So this is how the equations or parameters that we are going to calculate with respect to non-inverting and inverting. Ega, why let's try to compare inverting and non-inverting configurations. Almost all values same adava. I guess all values are same. No, the values here are different, then fine, issues. Okay, we'll do one thing. We'll take up one problem wherein we'll try to solve that problem for both inverting and non-inverting configurations, and let us try to figure out which configuration is better. When we say which configuration is better, it is not in terms of any power consumption agli mattondagli hangalla. When we talk about amplifier namdu yav amplifier better anlike yav parameter ನಾವು ನೋಡ್ತೀವಿ, it is always the gain. So ಎಲ್ಲಿ gain ಜಾಸ್ತಿ ಇರ್ತೈತಿ, that amplifier will be my suitable amplifier. ಅದಾದ್ಮೇಲೆ next we'll see about the input resistance. So ಯಾವ amplifiers ಒಳಗಡೆ input resistance ಜಾಸ್ತಿ ಇರ್ತೈತಿ, ಈಗ inverting amplifier ಒಳಗೆ input resistance ಜಾಸ್ತಿ ಬಂತಪ್ಪ ಅಂದ್ರೆ I'll go with inverting amplifier. Non-inverting amplifier ನಾಗ input resistance ಜಾಸ್ತಿ ಬಂತಂದ್ರೆ I'll go with non-inverting configuration. And the third one will be the output resistance. Yav amplifier naga output resistance kami irtati, I'll go with that. And the fourth one and the final one will be the bandwidth or the unity gain bandwidth. Of course, both the inverting and non-inverting configuration are having the same bandwidth, and in fact they are having the same output resistance also. So avu ಎರಡು parameter ಅಂತೂ ruled out. ಎರಡೂದ್ರಾಗೂ same value ಬರ್ತವ, irrespective of ನೀವು ಏನೇ parameters ಕೊಟ್ಟರು output resistance ಮತ್ತು unity gain bandwidth or the bandwidth will be same for both inverting and non-inverting configuration. But ನಾನು ಇಲ್ಲಿ ಏನು ನೋಡಬೇಕಾಗಿತ್ತು ಅಂತಂದ್ರೆ closed loop gain in terms of non-inverting configuration and inverting configuration ಯಾವುದು ಜಾಸ್ತಿ ಬರ್ತೈತಿ, ಅದು 1.2. ಇನ್ನೊಂದು input resistance, whether inverting amplifier has got input resistance ಜಾಸ್ತಿ ಅಥವಾ non-inverting amplifier ನ ಜಾಸ್ತಿ ಅದ, ಇದನ್ನ ನಾನು ನೋಡಬೇಕಾಗುತ್ತೆ. So if I do that, then I can do a clear-cut comparisons with respect to inverting and non-inverting configurations. So this is all about your entire set of derivation pertaining to op-amps, feedback amplifier, that is voltage series feedback amplifier, and voltage shunt feedback amplifier with respect to inverting and non-inverting configuration. And we have seen all the derivations, and we have solved all the numericals pertaining to these things. And the one thing which I was talking about, if I can just fine, so I'll just post it in the Teams, which is that you are supposed to solve it as an assignment. I'll just post it in the team. Now, before we commence or before we move ahead with the next concepts, so the next concept here would be the op-amp applications. So the applications of op-amp. So as you already know, op-amp has got various applications in its pocket, and basically the applications are categorized into 4 different aspects. One is general linear applications, the second one are filter and oscillator applications, the third one being comparator and detector applications, and the fourth one specially integrated circuit applications. So with these 4 categories, your entire syllabus is being bifurcated, and you are going to learn different applications, and we'll see in which category they are going to fit in, whether they will be fitted in general linear applications or filter and oscillator applications, comparator and detector applications, or special integrated circuit applications. We're going to see about them. So before that, let's just try to have a glimpse of can we have both AC as well as DC amplifications? Is it possible to have both the kind of amplifications given an op-amp. So of course there is a provision to have both AC and DC amplifications. So when we talk about DC amplifiers, here the output changes in response to changes in its DC input levels only. It is not going to consider the AC levels. ಯಾಕೆ ನಾ ಹೇಳ್ತಾ ಇದ್ದೀನಪ್ಪ ಅಂತಂದ್ರೆ, ಸಿ when we talk about any amplifier, ಈಗ ನಾನು opamp ಅಂತ ನೋಡಿದಾಗ, if I just look into inside the opamp is merely a differential amplifier. And ನಿಮಗೆ ಅಗದಿ ಪ್ರಿಸೈಸ್ ಆಗಿ ಹೇಳಬೇಕಪ್ಪ ಅಂತಂದ್ರೆ, opamp ನೀವು ಬ್ರೇಕ್ ಮಾಡಿ ನೋಡಿದ್ರೆ ಅಂದ್ರೆ ಒಳಗಡೆ ಟ್ರಾನ್ಸಿಸ್ಟರ್ ಬಿಟ್ಟರೆ ಬೇರೆ ಏನು ಇರಂಗಿಲ್ಲ. And transistors anta ಹೇಳಿದಾಗ there could be MOSFETs or there could be BJT. And if I consider MOSFET or if I consider BJT, ಈಗ ಟ್ರಾನ್ಸಿಸ್ಟರ್ ಅಂತ ಬಂದಾಗ ಟ್ರಾನ್ಸಿಸ್ಟರ್ ಗೆ ನಾನು I will be using both AC voltages or AC supplies or AC as well as DC. ಯಾಕಪ್ಪ ಅಂತಂದ್ರೆ ಯಾವುದೇ ಒಂದು ಟ್ರಾನ್ಸಿಸ್ಟರ್ to ensure it is operating or it is behaving as an amplifier, first I should bias it in the proper region with the proper DC voltages. Remember this. ಯಾವತ್ತೂ ನಂದು ಟ್ರಾನ್ಸಿಸ್ಟರ್ ಆಂಪ್ಲಿಫೈರ್ ಆಗಿ ವರ್ಕ್ ಆಗ್ಬೇಕಪ್ಪ ಅಂತಂದ್ರೆ ನಾನು ಅದಕ್ಕೆ DC ವೋಲ್ಟೇಜ್ ಕೊಟ್ಟು ಅಂಡ್ ಒಂದು ಪರ್ಟಿಕ್ಯುಲರ್ ಏರಿಯಾ ಆಪರೇಟಿಂಗ್ ಏರಿಯಾನಾಗ ಅಥವಾ ಆಪರೇಟಿಂಗ್ ರೀಜನ್ನಾಗ ಅದನ್ನ ಪುಷ್ ಮಾಡಬೇಕು. ಅಲ್ಲಿ ನನಗೆ DC ವೋಲ್ಟೇಜ್ ಕೆಲಸಕ್ಕೆ ಬರ್ತೈತಿ. ಆಮೇಲೆ ಆಂಪ್ಲಿಫಿಕೇಶನ್ ಅಂತ ಬಂದಾಗ ನಾನು AC ಇನ್ಪುಟ್ ಕೊಡ್ತೀನಿ, ಆ AC ಇನ್ಪುಟ್ ಆಂಪ್ಲಿಫೈ ಆಗುತ್ತೆ. So this is how any amplifier or any transistor will consume or will have the or basically they will need both AC as well as DC voltages. But suppose ನನಗೆ ಬರೀ DC ಅಷ್ಟೇ ಆಂಪ್ಲಿಫೈ ಮಾಡೋದಿತ್ತು ಅಥವಾ ಬರೀ AC ಅಷ್ಟೇ ಆಂಪ್ಲಿಫೈ ಮಾಡೋದಿತ್ತು ಅಂತಂದ್ರೆ ಆ ಇನ್ನೊಂದು ಸಪ್ಲೈ ನಾನು ಏನ್ ಮಾಡಬೇಕು? I should ensure that is not it is not going to affect the other supplies. ಈಗ ನಾನು AC amplifiers ಅಂತ ಮಾಡಿದಾಗ ಅಲ್ಲಿ DC ಸಪ್ಲೈನೂ ಇರ್ತೈತಿ, ಯಾಕಂದ್ರೆ ಬಯಾಸಿಂಗ್ ಆಸ್ಪೆಕ್ಟ್ ಸಂಬಂಧ ನಾನು DC ಸಪ್ಲೈ ಯೂಸ್ ಮಾಡಿರ್ತೀನಿ. ಬಟ್ ನಾನು DC ಆಂಪ್ಲಿಫಿಕೇಶನ್ ಆಗ್ಲಾರ್ದಂಗ ನೋಡ್ಕೋಬೇಕು. ಸಿಮಿಲರ್ಲಿ when I talk about AC amplification, ಅಲ್ಲಿ DC ಕಂಪೋನೆಂಟ್ ಇದ್ದೇ ಇರ್ತೈತಿ, ಅದನ್ನ ಬಯಾಸಿಂಗ್ ಮಾಡಿ ಆ ಬಯಾಸಿಂಗ್ ಪಾಯಿಂಟ್ ನ ಲಾಕ್ ಮಾಡಬೇಕು. ಸೊ ದಟ್ ಓನ್ಲಿ AC amplification will work. So that is the basic thing that one has to take care in DC and AC amplifiers. So DC amplifiers can be inverting, non-inverting or differential. And to reduce the output offset voltage to 0, that is to improve the accuracy of the DC amplifier, the offset null circuitry of the op-amp can be used. This is one very important aspect. ಈಗ ನಾನು accuracy ನಾನು ಯೂಸ್ ಮಾಡಬೇಕಪ್ಪ ಅಥವಾ output offset voltage ಅಂದ್ರೆ ಏನು? See, basically op-amp is a differential amplifier. ನಾನು ಎರಡೂ ಇನ್ಪುಟ್ಸ್ ಗೆ ಸೇಮ್ ವೋಲ್ಟೇಜ್ ಕೊಟ್ಟನಪ್ಪ ಅಂತಂದ್ರೆ ನನಗೆ ಡಿಫರೆನ್ಸ್ 0 ಆಗುತ್ತಾ, ಔಟ್ಪುಟ್ ಶುಡ್ ಬಿ 0. ಬಟ್ ಆಕ್ಚುಲಿ ಪ್ರಾಕ್ಟಿಕಲ್ ಕೇಸ್ನಾಗ ಹಂಗ ಆಗಂಗಿಲ್ಲ. ದೇರ್ ಇಸ್ ಅ ಸ್ಮಾಲ್ ವೋಲ್ಟೇಜ್ ವಿಚ್ ವಿ ಕಾಲ್ ಇಟ್ as a output offset voltage, small offset voltage. ನಾನು ಅದನ್ನ ಬಿಫೋರ್ ಐ ಸ್ಟಾರ್ಟ್ ಯೂಸಿಂಗ್ ದಿ op-amp as some application, I should make the output voltage to 0. ಅದನ್ನ ನಾ 0 ಮಾಡಬೇಕಪ್ಪ ಅಂತಂದ್ರೆ I should be using a circuit called as null circuitry, which will come with the op-amp. ಅಥವಾ op-amp ನಾಗ ನಾನು op-amp circuit ನಾಗ ಒಂದು ಸ್ಮಾಲ್ modifications ಮಾಡಿ, ನಾನು ಅದರ modifications ಯಾಕೆ ಮಾಡ್ತೀನಪ್ಪ ಅಂತಂದ್ರೆ ಬಿಫೋರ್ ಐ ಅಪ್ಲೈ ದಿ ಆಕ್ಚುಯಲ್ ಇನ್ಪುಟ್ಸ್ ಮೈ ಔಟ್ಪುಟ್ ಶುಡ್ ಬಿ 0. ಯಾಕಂದ್ರೆ ನಾನು ಇನ್ಪುಟ್ ಏನು ಕೊಡ್ಲಿಲ್ಲ ಅಂದ್ರೆ ಔಟ್ಪುಟ್ 0 ನೇ ಬಂದಿರಬೇಕು, ಅಥವಾ ಇನ್ಪುಟ್ ಸೇಮ್ ಕೊಟ್ಟಾಗ ನಾನು ಔಟ್ಪುಟ್ 0 ಬಂದಿರಬೇಕು. ಅದು ಆಕತೆ ಇಲ್ಲ ಅಂತ ಚೆಕ್ ಮಾಡಬೇಕು. ಅದು ಆಗ್ಲಿಲ್ಲ ಅಂತಂದ್ರೆ ನಾನು null circuitry ಯೂಸ್ ಮಾಡಬೇಕು. So a null circuitry use ಮಾಡ್ಲಿಕ್ಕೆ whatever circuit I am going to use it, that has to be maintained. So this will ensure the accuracy of the amplifier is improved. For op-amp without op-amp null circuitry, ಈಗ particular op-amp ಗೆ they will come with an automated or they will come with an inbuilt null circuitry. But ಕೆಲವೊಂದು op-amp they won't come with inbuilt null circuitry. On that time ನಾಗ external offset voltage compensating network should be used. Preferably, usually ನಾವು ಏನು ಯೂಸ್ ಮಾಡ್ತೀವಿ, ಒಂದು ಸ್ಮಾಲ್ ರೆಸಿಸ್ಟೆನ್ಸ್ ಯೂಸ್ ಮಾಡಿರ್ತೀವಿ. ಸೊ ದಾಟ್ ರೆಸಿಸ್ಟೆನ್ಸ್ ಇಟ್ ಸೆಲ್ಫ್ ವಿಲ್ ಬಿ ಆಕ್ಟಿಂಗ್ ಆಸ್ ಎ ಕಂಪೆನ್ಸೇಟಿಂಗ್ ನೆಟ್ವರ್ಕ್. ಅದನ್ನ ಯೂಸ್ ಮಾಡಿದಾಗ ಒಂದು ಪ್ರಾಪರ್ ವೇನಾಗ ವಿ ಕ್ಯಾನ್ ಸಿ ದಟ್ ಬಿಫೋರ್ ಇಫ್ ವಿ ಡೋಂಟ್ ಅಪ್ಲೈ ಎನಿ ಇನ್ಪುಟ್ ಆರ್ ಅ ಕಾಮನ್ ಇನ್ಪುಟ್ ಅಪ್ಲೈ ಮಾಡಿದಾಗ ಬೋತ್ ಟರ್ಮಿನಲ್ಸ್ ಗೆ ಔಟ್ಪುಟ್ ವಿಲ್ ಬಿ ಆಟೋಮೆಟಿಕಲಿ ಕಮಿಂಗ್ ಡೌನ್ ಟು 0. ಅದು ಆಗೋ ತರ ನೋಡ್ಕೊಳ್ಳೋಂಗ್ ಮಾಡುತ್ತೆ. ಸೊ ದಿಸ್ ಇಸ್ ಬೇಸಿಕಲಿ ದ ಫಂಡಾ ಆಫ್ ದಿ null circuitry or compensating network. So when it comes to AC amplifiers ಅಂತ ಬಂದಾಗ, see if I just want to talk about AC amplifiers. Op-amps can be used for AC amplifications as well, provided we use coupling capacitors to suppress the amplification of DC levels that are produced due to thermal variations and drifts, as well as the biasing conditions also. ಈಗ ನಾನು the op-amp as an amplifier, but I want to amplify only AC, but I don't want to amplify DC. At that time naga I will be using something called as coupling capacitor. So coupling capacitors will play a crucial role in stopping the DC component entering the op-amp, thereby DC components won't be amplified. So this is what basically is the things that are present in the AC amplification and DC amplifications. So with this, let's go ahead with a small gist of applications, and I'm going to cover in a quick span of time all these three applications, which we already know it, and it is very easy to understand as well. Summing amplifier, scaling amplifier, averaging amplifier, for both inverting configuration as well as non-inverting configuration. And this is exactly the same thing what you have learned in your basic electronics course. ಆ ಡಿಫರೆನ್ಸ್ ಏನಪ್ಪಾ ಅಂದ್ರೆ ಭಾಳ ನೀವು R1 R2 R3 ಅಂತ ಯೂಸ್ ಮಾಡಬಹುದು, ಇಲ್ಲಿ RA RB RC ಅಂತ ಯೂಸ್ ಮಾಡ್ತೀರಿ. ದಟ್ ಈಸ್ ದ ಡಿಫರೆನ್ಸ್. ಅದು ಬಿಟ್ರೆ ಬೇರೆ ಹೆಚ್ಚಿಗೆ ಏನು ಡಿಫರೆನ್ಸ್ ಇಲ್ಲ. ಸೊ ವಾಟ್ ಈಸ್ ಮೈ summing amplifier? So let us try to go ahead with one particular configuration, inverting or non-inverting. You can just see over here, since I am giving the input voltage, that is VA, VB, VC are my three inputs given to the inverting terminal through the resistors RA, RB, RC. Hence this is summing amplifier or adder circuit or inverting summing amplifier. So basically this has got three inputs, three resistors and one feedback resistance, and the output voltage is taken across load resistance. Now I was talking about something called as the offset minimizing concept. So this is what is the offset resistor that I used. Idu use yadike use madinappa antandra, ee resistor use ಮಾಡೋದ್ರಿಂದ ನನಗೆ if I apply a same voltage, or by chance if I apply V2 or V1 ಎರಡು voltage same ಬಂತಪ್ಪ ಅಂತಂದ್ರ ನನ್ನ output voltage automatically 0 ಆಗುತ್ತೆ. If I don't use this ROM, that is offset minimizing, if I don't use this, if I just directly connect it to ground, plainly to ground, which we usually do it in our lower classes, ನಾನು ಹಾಗೆ ಮಾಡ್ತೀವಿ, ಡೈರೆಕ್ಟ್ಲಿ ನಾನ್ ಇನ್ವರ್ಟಿಂಗ್ ಟರ್ಮಿನಲ್ ತಂದು ಗ್ರೌಂಡ್ ಕನೆಕ್ಟ್ ಮಾಡ್ತೀವಿ. ಅದು ಮಾಡಿದಾಗ that is not a practical scenario. ಅವಾಗ ನನಗೆ ಈ ಟರ್ಮಿನಲ್ ಮತ್ತು ಈ ಟರ್ಮಿನಲ್ ನಡುವೆ ಎರಡು ವೋಲ್ಟೇಜ್ ಸೇಮ್ ಅಂತಪ್ಪ ಅಂತಂದ್ರೆ output voltage won't be nullified. Difference voltage should be 0 ಬರಂಗಿಲ್ಲ. ಸೊ 0 ಬರಬೇಕಪ್ಪ ಅಂತಂದ್ರೆ ನಾನು ಇಲ್ಲಿ I calculate this resistance and I attach a resistance over here, and that will ensure that the moment common mode signals are coming over here, the different signals are coming, and that will make my offset voltage to 0. And what will be the value of ROM, that is offset minimizing resistor? It is nothing but the parallel combination of RF, RA, RB, RC. ಇವೆಲ್ಲ ನಾಲ್ಕು ರೆಸಿಸ್ಟರ್ಸ್ ಪ್ಯಾರಲಲ್ ಕಾಂಬಿನೇಷನ್ಸ್ ತೆಗೀರಿ, ವಾಟ್ ಎವರ್ ಇಸ್ ದಿ ವ್ಯಾಲ್ಯೂ ಆ ರೆಸಿಸ್ಟರ್ ತಂದಿಲ್ಲ ಅಟ್ಯಾಚ್ ಮಾಡ್ರಿ, that will make your offset voltage come to 0. So that is the basic setup. Fine. So if I just go ahead and try to analyze a very simple two-step analysis, again Kirchhoff's current law apply ಮಾಡ್ತೀನಿ first ಗೆ. Current entering a node is equal to current exiting a node. So I'll consider this node because here is my voltage, input voltage is connected over here. ಎಲ್ಲಾ voltage ಇಲ್ಲೇ ಬಂದು ಇಲ್ಲಿಂದ ನಾನು op-amp ಒಳಗಡೆ ಹೋಗ್ತಾವ. ಸೊ ಈ ನೋಡ್ಗೆ ಯಾವ ಕರೆಂಟ್ಸ್ ಬರ್ಲಿಕ್ತಾವ? ಒಂದು IA ಬರ್ಲಿಕ್ತದ, ಒಂದು IB ಬರ್ಲಿಕ್ತದ, ಒಂದು IC ಬರ್ಲಿಕ್ತದ. ಅಂಡ್ ಈ ನೋಡಿಂದ ಹೊರಗಡೆ ಯಾವ ಕರೆಂಟ್ ಹೊಂಟೈತಿ? IF ಹೊಂಟೈತಿ. So that is the case, then if I calculate IF is equal to IA plus IB plus IC, or IA plus IB plus IC is equal to IF. And like I was telling in my previous class, Kirchhoff's voltage law, and if I take a resistance between two voltages, what will be the current? Starting point minus next point divided by the resistance, that is V1 minus V2 divided by R. So similarly, ನನಗೆ IA calculate ಮಾಡಬೇಕಪ್ಪ ಅಂತಂದ್ರೆ VA minus V2 divided by RA. So that's what is the resultant, VA minus V2 divided by RA. ಇದ್ರದ್ದು ಹಂಗೆ ಆಗುತ್ತೆ, VB minus V2 divided by RV. ಇದ್ರದ್ದು ಹಂಗೆ ಆಗುತ್ತೆ, VC minus V2 divided by RC. But since V2 is virtually grounded, from the concept of virtual ground, the other terminal ಇದು ಎಲ್ಲಿ ಕನೆಕ್ಟ್ ಆಗೈತೆ ನೋಡ್ರಿ, it is connected to ground. ಇದು ಗ್ರೌಂಡ್ ಕನೆಕ್ಟ್ ಆಗೈತಪ್ಪ ಅಂತಂದ್ರೆ ಇದರದ್ದು ಪೊಟೆನ್ಶಿಯಲ್ 0 ವೋಲ್ಟ್ ಆಯ್ತು. So if this is 0 volt, then this will also be 0. ಸೊ ಆ ಲೆಕ್ಕದಾಗ VA minus V2 divided by RA ಅಂತ ಮಾಡಿದಾಗ V2 term will be 0. ಏನ್ ಮಾಡುತ್ತೆ ನಾನು VA minus V2 divided by RA ಅಂತ ಮಾಡಿದ್ದೆ. So V2 has gone to 0. So that makes my this first equation of IA as VA by RA, and that's what I have written over here, VA by RA. Similarly, IB will be equal to VB by RB, and so is the case with VC, that is IC, VC by RC. If that is the case, and what will be the value of IF? IF will be what? V2 minus V0 by RF, and V2 is 0. That makes me this 0. So minus V0 by RF. So if I just arrange it in a manner, minus V0 by RF equal to VA by RA plus VB by RB plus VC by RC, or V0 is equal to, I'll push RF to all the terms, RF by RA, RF by RB, RF by RC. So this will give you the summing concept or the output voltage wherein all the voltages are getting added, and minus sign indicates it is a inverting amplifier. And to move ahead, to simplify, if I assume that all the resistances RA, RB, RC, RF are all equal to one particular value R, and I substitute that LL, RF, RA, RB, RC ಅದಾವ ಎಲ್ಲ ಕಡೆ R ಅಂತ ಹಾಕ್ಬಿಟ್ಟಪ್ಪ ಅಂದ್ರೆ, ಅಥವಾ RF ಒಂದು ಹಂಗೆ ಇಡೋಣ, RA, RB, RC ಜಾಗದಾಗ R ಅಂತ ಹಾಕಿದ್ನಂದ್ರೆ what is that amount to get? R will be there in the denominator. I'll take it out common, minus RF by R multiplied by VA plus VB plus VC. So that will be my summing amplifier. So this is how the summing amplifier works. Now the extended version of the summing amplifier is what? Scaling amplifier and averaging circuit. Scaling amplifier ಅಂತಂದ್ರೆ ಏನಪ್ಪಾ, ನಾ ಇಲ್ಲಿ ಏನ್ ಮಾಡಿದೆ, ಏನು ಸಿಂಪಲ್, ಇಲ್ಲಿ ಏನ್ ಮಾಡಿದೆ ನಾನು RA, RB, RC ಎಲ್ಲಾ ತರದ್ದು ವ್ಯಾಲ್ಯೂ ಸೇಮ್ ಅಂತ ತಗೊಂಡ್ರೆ ನನ್ನ ಔಟ್ಪುಟ್ ಹಿಂಗ್ ಬಂತು. ಸಪೋಸ್ ಎಲ್ಲಾ ತರದ್ದು ವ್ಯಾಲ್ಯೂನ ಸೇಮ್ ತಗೊಳ್ಳಿಲ್ಲ ಅಂತಂದ್ರ, if RF by RA, RF by RB, RF by RC equal ಇರ್ಲಿಲ್ಲ ಅಂತಂದ್ರೆ it is going to retain the same equation. ಹೌದಾ? ಸಿ ಇದು ನನ್ನ ಸಮ್ಮಿಂಗ್ ಆಂಪ್ಲಿಫೈರ್, ಇದ್ರೊಳಗಡೆ RA, RB, RC ಈಕ್ವಲ್ ಆಯ್ತಪ್ಪ ಅಂತ ಹಿಂಗ್ ಬಂತು. ಸೊ ದಿಸ್ಕ್ ನಾನು ಏನಂತೀನಿ ಸಮ್ಮಿಂಗ್ ಆಂಪ್ಲಿಫೈರ್ ಫೈನಲ್ ಇಕ್ವೇಶನ್. ಬಟ್ ಅದೇ ಇವು ಯಾವ ವ್ಯಾಲ್ಯೂಸ್ ಈಕ್ವಲ್ ಆಗ್ಲಿಲ್ಲ ಅಂತಂದ್ರೆ ಇಟ್ ಈಸ್ ಗೋಯಿಂಗ್ ಟು ರಿಟೈನ್ ಇಟ್ಸ್ ಒರಿಜಿನಲ್ ವ್ಯಾಲ್ಯೂ. ಸೊ ಆ ಒರಿಜಿನಲ್ ವ್ಯಾಲ್ಯೂ ಏನ್ ರಿಟೈನ್ ಮಾಡಿರ್ತೈತಲ್ಲ ಈ ಇಕ್ವೇಶನ್, ದಿಸ್ ಇಸ್ ಕಾಲ್ಡ್ ಆಸ್ ದಿ scaling or weighted amplifier. So and this becomes scaling amplifier. So nim scaling amplifier anta question keladaga you are supposed to do the same thing with respect to the summing amplifier. Just extend one sentence saying that all are not equal. So that's about your scaling amplifier. And the last one, averaging circuit. Averaging circuit nag ನಾನು ಅದೇ ಮಾಡಿದೆ. averaging circuit nag ಏನು ಮಾಡಿದೆ ನಾನು, summing amplifier ಅಲ್ಲಿ RA, RB, RC equal to R ಇರ್ತಾವ, and input is amplified and it should be equal to 1. RF by R term ಏನದಲ್ಲ, it is equal to N. N indicates there are 3 resistances and it will be divided by 3. So that gives you the averaging amplifier or averaging circuit. So averaging circuit agli, scaling amplifier agli, they are the extended version of the summing amplifier, and all these are with respect to inverting configuration. So that's what sums up your some small 3 applications of inverting amplifier configuration. So in the next class we're going to say same summing, scaling, averaging circuits, but with respect to non-inverting amplifier configurations. And adamele we're going to see the comparators, Schmidt-Trigger instrumentation amplifiers, and then zero crossing detector. So some 4 to 5 applications remaining that we'll see in the subsequent next class. So this is all about your today's class. So we'll stop it here, and then we can continue it in the next class. So just try to give the attendance. The attendance link is the same attendance link. I'll just I have opened up the attendance. Just type the same attendance. The attendance link will be the same. The code will be the code is 9848. 9848. 9848 is the code. (9848) is the code. 9848 is the code. Please give the attendance quickly. So with this, we'll conclude today's session, and preferably we'll meet in the subsequent class. If there are any class slots that are vacant, and if I want to engage it in the subsequent gap hours, I'll inform you, and please try to join, because the contents and the concepts are very vast, and I don't want to miss upon any of the classes. We can slowly and steadily, by understanding every concepts, we can work upon those things, and we can conclude, or you can understand the contents of the entire syllabus in a greater depth, and see that you score good marks in the examination as well. So we'll stop it here, so we can meet again in the next class. So those who have given the attendance can skip from the class. So thank you for the patience listening. We can meet in the next class.
Thank you, sir.
Thank you, sir.